Thank you for having me here. And I will be talking today about a project that has just started recently. So I want to first give a disclaimer. Almost everything I'm going to say today is purely conjectural, and I will give no proven claims. So don't be mistaken to think that anything has been proven. What we are going to do is describe an outline for a project that takes real THH and real algebraic K-theory and tries to do it in a purely infinity categorical fashion. Okay? Okay. So what I want to start with is two very easy remarks. I want to make everything very clear, because I don't want anyone to lose me on these points. So I first want to speak about duality structure. We, of course, talked about it a lot already in this workshop. So let's say I have a category, or I don't know, infinity category, simplicial space, anything that is directional in any way. So I can speak about a Z-mod 2 action on X. Let's say a strict Z-mod 2 action, because it doesn't matter for this point. And I can think about it in the following way: I take X, and there is an endomorphism of X, sigma, and then when I do it twice, I get back the identity. Okay? This does not matter for this point, and this is why it's just a very relaxed statement about the difference between a Z-mod 2 action and a duality. Okay, just so what is the difference between a Z-mod 2 action and duality? Duality looks very similar, only X here I want to write X op. Okay, this is the only point I want to make. That, and here I can take tau op. I get back X, and I want to get the identity in any way that you want to say it. Okay, but this is the difference. That in a duality we have X op, and in a Z-mod 2 action we have X here. Okay, this is the first thing I want to address, and the second thing I want to address is the difference between so-called naive group actions or so-called genuine group actions. I'm pretty sure that most people here know this very well, but I just want to make this clear. So let's say that G is a finite group. Okay. So what is a naive G space? So it's just a space X with an action of G, and we consider X up to weak homotopy equivalence. What does this mean? So when are two G spaces considered equivalent? When we have a map, let's say F, that is G equivariant, and only after I forget the G action, I have an equivalence of spaces. Okay? So the map should be equivariant, but the equivalence itself doesn't really consider the G action. And this is this information, and a G space up to naive equivalence is giving this information is equivalent to giving a functor from BG to topological spaces, and we call this functor X, and then we can think about X as the G space in a naive way. Okay, and what can we do with a naive G space if we have a subgroup H of G? We can take the homotopy fixed points with respect to this subgroup. Okay, so this is the naive approach. What is the genuine approach? So again, we want a space X with an action of G, but now we want to consider it up to strong homotopy equivalence. What is strong homotopy equivalence? So let's say we have another space Y with a G action, and again, we want an equivariant map F. Okay? So what does it mean that X and Y are equivalent? It means that we have a map on the other side, let's call it, I don't know, H, such that if we look at F composed with H, this is homotopic. This is homotopic via G maps to the identity on X. Okay? And the other way around. So the homotopy should go through G maps. Okay? Here, it's you can say the same thing, only the homotopy doesn't have to go through G maps. This is the difference. Okay, and what is this information of a genuine space with G action equivalent to? So this is Elmendorf's theorem, that this is equivalent to a presheaf of spaces on what's called the orbit category of G, so just a functor from here to topological spaces, and the orbit category of G has objects which are finite orbits of G, things that look like this as G sets. Oh, right, not everybody can see. Okay. Okay, so these are orbits, okay, and I think of them as G sets, and maps are just G equivariant maps. So this is this category, and the information of a strong or genuine G space is just a presheaf on this category. This is this is a point mod G. Yeah. What? In what notation? Oh, in here. I'm not really sure what this means, but okay. Yeah, yeah, but I think that what you probably meant is that there is a functor from this category to this category, and here there is a connected component or an object with G automorphisms, and this object with G automorphisms is G mod a point. Yeah, G mod E. Yeah, that's maybe what I need to say. Yes, okay, yes. But you need to think about what in what sense, yeah. Okay. And just one last remark. How do we need to think about this how do we need to think about this presheaf of spaces? So each object, each orbit, G mod H, goes to a space that I should think about. Okay, so let's call this genuine space X, and I should think about the space corresponding to the orbit G mod H as the H fixed points of X. Okay, so this has not a lot to do with this. Okay, I can, if I have a naive G space, I can take homotopy fixed points, and if I have a genuine G space, I can take the H fixed points, but there is no real relation between the two. I can put something very different than this here. Okay? Great. And just and I said all this about spaces because it's easier to understand in the context of spaces, but this works in a lot of contexts. Like you can speak about a naive G category or a genuine G category. You can speak about a naive G spectrum or a genuine G spectrum. It becomes a little more complicated, but this. Excuse me? A genuine G spectrum is not such a functor. It's not such a functor. When I say genuine G spectrum, I don't mean a functor in this category. I mean something else, which I don't want to explain at the moment. Okay? Yeah. I can say I mean a spectral Mackey functor on the effective Barentside category of G. Okay? Yeah.
So is the idea going to be that, like, the opinion quotes that x to the h equals that will sort of go based on the same equations as, like, the x to the h versus when I change the
The structure of this category says that when you look at this Presheaf, then you have certain compatibility between the different fixed points, right? For example, if you have an h fixed point and you have a subgroup that's larger than h, then it. Hold on. If you have a subgroup smaller than h, then it's going to still be a fixed point, okay, for this smaller subgroup, okay? But so you have such compatibilities that come from the structure of this category, okay? So this is just to set the language and to not get confused by things that are actually simple. Okay, the next thing I want to do is to quickly go over the classical. I say classical; it's just in the past few years, but the classical versions of real algebraic theory and real THH. So these were first developed by Lars, who is here. No, and Ib Madsen. I thought that it would be fun to to have him here. And Ib Madsen and Emanuele developed them. And okay, so let's just okay. So put a title. We call real K-theory in this lecture KR, and we call real THH THR. Okay, so let's go over it quickly, just so we know what we're starting from. So what is the input for KR? It's, let's call it E, an exact category with a duality structure. Okay, so what is it? It's a functor from E to E op, and E op still has an exact structure, and this duality structure just needs to be an exact functor. Okay, so this is the input for real algebraic K-theory, and what is the output? It means, yeah, it means isomorphic. Okay, there are several different concepts. There is a strict duality, and there is a non-strict duality, and dualities can be strictified in certain situations. So, but yeah, the concept is that you need to be isomorphic, naturally isomorphic to the identity after you compose the two. You take tau and tau up. Excuse me? Okay, so maybe, yeah, mostly when I say category in this conversation, in this talk, I mean infinity category, but here I really mean a one category. Okay, this is the context that I speak about here, and the idea would be to generalize this to infinity categories, but here it's one category. Okay, so what is the output? So we take KR, we plug in E. What do we get? So if we didn't have this R here, we would just get a spectrum. But here we want a spectrum with a Zemo2 action. Okay, so the output is a genuine Zemo2 spectrum. I didn't explain exactly what it means. I said the words. spectral Mackey functor and the effective Burnside category of this group. But I don't want to exactly explain what it means. Yeah, but there is an equivalence between you can give different models for the same thing for a genuine Zeeman-2 spectrum, but on the abstract level, if you think about what goes up in heaven, it's the same thing, right? So you can excuse me. Maybe it's not heaven, I don't know, but it's just different ways to codify the same thing, okay? Okay, so where was I? Yes, so you get a genuine Zeeman-2 spectrum. So yeah, in the classical construction, you don't really get a spectral Mackey functor. You get something else. Maybe I can just say it very quickly. You get a spectrum that you can deloop not only in the direction in the usual direction of spheres, but also in a direction called let's say we have a non-trivial element here. Okay. So we have a representation, a Zeeman-2 representation that corresponds to this element, just flipping the sign representation, and then you take the corresponding sphere, and then you can deloop in the direction of this sign sphere. Okay, this is the data that you get. Okay, so this is real algebraic K-theory, and let's talk about THR. What is the input for THR? So it's just a category, C. Now I mean one category, but it's enriched in symmetric spectra. And also it has a duality structure, which gives us the real structure on THR. Okay, and again the output is a genuine Zeeman-2 spectrum. I have some room here. Okay, so this is just a very, very general picture of. I'm not giving the construction. I'm not giving anything. I think Lars will talk about it on Friday, right? Okay, so just to see what we're dealing with, and okay, so we want a sort of connection between algebraic K-theory and THH, also in the real setting. So let's take an example that is applicable in both cases. So let's focus on a simple example to begin with. Just let's take a ring with anti-involution. Involution, just a plain old ring, algebraic, nothing special. And so what is this anti-involution? It's a ring homomorphism. Let's call it tau. From A to A up, it's like a duality structure, such that tau up composed with tau is the identity. Okay? And why is this actually a special case? Okay, so if I look at the category of projective finitely generated modules over A, it has several structures. One structure that it has it is an exact category with duality, okay, like was explained many times in the past 2 or 3 days, and yeah, so we can take its so the duality comes from this anti-involution, okay, and we can take its real algebraic K-theory, and this is what we call, or vice versa, this is what we call the real algebraic K-theory of the ring with involution A. Okay, but how do we define the real THH of A? So we can take this category and we can do take the Eilenberg-MacLane functor, okay, and this takes an exact category with duality, and it gives us an enrichment not over a billion groups, but over symmetric spectra. Okay, the Eilenberg-MacLane functor takes an abelian group to a symmetric spectrum, so we get an enrichment. So this is enriched over symmetric spectra. Still has a duality. Yes. So we still have a duality. This remains. So now we can take THR of this category, and this is what we call THR of A. Okay, and in this context where we have both real algebraic K-theory and real THH, we can have a trace map. So this is the real Dennis trace map that goes from K-theory to THH. So there is also a real version of this trace map. So this is the picture. Again, I did not explain all the details or any of the details really, but this is the picture of what goes on, and we want to create a similar picture in a context that is more generalized than just a ring with anti-involution. Okay, so let's. Excuse me, 1 second. We finished the technical part. Okay, what is the question? I'm sorry.
Why does that not work? Why can you not just say that way in the exact category?
To say. Yeah, I can, but the thing that I want to present is much easier to present in the context of one object. So I want to concentrate on the example of rings and do this homotopically, and then maybe later there will be a multi-object version and so forth. Yes. How is the exact structure? Yeah, this is all Emanuele's thesis. Just I wrote it down very, very fast. Now I have to erase. Okay, so I'm sorry. This is one of the first times. Yeah. This one. Let's try. Let's try. Let's try. I'm feeling adventurous. I will get to this. I will get to this. I mean, this is the whole subject of the lecture, actually, to try to give some hint of what these things should be. I really don't know why you do this in Germany. Takes so much. Excuse me? Okay. Okay, so let's try to generalize. Okay, so in what way do we want to generalize? So the slogan is we're looking for something that, okay, so here we have a ring with anti-involution, okay? So what are we looking for? What is the homotopical version of a ring? It's an E1 spectrum, okay? And we want it to have an anti-involution, okay? But as I will explain later, we wanted to have a genuine anti-involution, whatever that means. We will try to hint at what this means later. So looking for an E1 spectrum with a genuine anti-involution. Okay, this is what we want in the end. Yeah, sorry. Yeah. E1 like this, yes. This is what we want. Okay. So, in some sense, the side for the input for real K-theory is going to be a little simpler, even though it's really much more complicated. But a lot of work has been done on this. So let's look at the input for KR. So what we're going to want is infinity Waldhausen categories. Yeah? Oh, the other thing? Oh, I'm short on time. Okay. I will say this quickly. So algebraic K-theory, already in the 70s, Waldhausen put it in the context of Waldhausen categories, which are some sort of categories with weak equivalences and cofibrations. And the cofibrations, they replace the admissible monomorphisms in the case of exact categories. And then Clark Bowick, in recent years, he generalized this for infinity Waldhausen categories. And he described algebraic K-theory as some sort of universal functor on the infinity category of infinity Waldhausen categories. And also, about 2 years ago, the same guy, Clark Bowick, did an equivariant version of this. He defined G-equivariant infinity Waldhausen categories and defined G-equivariant algebraic K-theory as a functor from the infinity category of those to the category of genuine G spectra. And this is all very, very good, but it doesn't really solve our problem because we don't really want a Zemo 2 equivariant version of algebraic K-theory. We want a twisted Zemo 2 equivariant version of algebraic K-theory as was written here, and I erased. But the point is that if we take something that's really Zemo 2 equivariant, we don't get the op there in the middle. We want something twisted. So one task for this project is to find the correct definition for an infinity Waldhausen category with genuine duality. Okay, so this doesn't exist yet. This needs to be defined, and then real K-theory will be a functor from the infinity category of those two genuine Zemo 2 spectra. Okay, so this is the K-theory side. Let's talk a little more about the unless maybe there are questions. Okay, so. This is the question. I really don't know at the moment. I'm just saying that this is the question. Oh, so you're suggesting that the best concept here should be an exact infinity category?
Yeah, I mean the dual of a cofibration is.
Yeah, it's I understand. Okay. Okay, so the suggestion here is that we should take something that when you take the opposite category kind of keeps its structure, and maybe this is not the best idea. Okay. But in any case, we want the input for real algebraic K-theory to be something that if we take such an E1 spectrum with a genuine anti-involution, and we take projective modules, projective finitely generated modules over it, whatever this means, would give us such a category. Okay, this is a property that this sort of category should satisfy. Yeah. Okay, so this is the main part of my talk, and I'm getting to this now. Okay, great. How much time do I have? Half an hour. Great. So this is perfect for what I want to talk about. Okay, so let's start to think about what an E1 ring spectrum with genuine anti-involution is. Okay, so I want to take this approach and change it a little bit. Okay, when you have so we said that the input for THR is a category enriched over symmetric spectra with duality. Let's think about what happens when this category has only one object. Okay, what do we get? So if C is a category enriched in symmetric spectra with duality and one object. Let's call it C. Okay? So we can denote by A the endomorphisms of these objects and what sort of structure exists on A. So first of all, it's a symmetric spectrum. Second of all, there is a composition, which gives it an E1 structure. So this is an E1. I think I don't really want to work strictly here. No, just because the only reason I'm speaking like this is because this is the context in which this was originally defined. But the real goal is to do this all in a model independent way, and to do this really infinity categorically. Okay. So let's write this. E1 algebra in symmetric spectra. Now there's no confusion, right? This is. I don't care really, but because everything that we're going to do is going to be model independent in the end. It's not going to care about this is whether I think this doesn't care whether this is a symmetric spectrum either. It's just a way to construct it in a way that's convenient, and then you can prove theorems. But really, it doesn't care. You don't really need the model to calculate THR. Okay, but let's do this for the sake of just not doing anything too risky. Okay, so this is first of all an E1 algebra in symmetric spectra. But there is another structure, right? There is a duality structure on C, and this gives us a duality structure on the endomorphisms of any object. So we get with anti-involution. Involution tau from A to A op. So what does this really mean? Okay, so when we have an E1 algebra, we can look at its opposite. The E1 operad has a twisting. You can just reverse the order of the entries, and when you compose with this, you get the opposite algebra. Okay, and this is just a map of E1 spectra from A to A op. This is the structure that we get in the case of one object. Yes, yes, and also if you take T op and compose it with T, it should be isomorphic to the identity on. It's now a self map. Maybe it should be actually equal. I'm not really sure. Need to think about this for a second. Yeah, so this is a spectrum. Yeah, so I mean homotopic. Yes, I mean homotopic because. Yes, I think you get it. Yes, because. Okay. Okay, so let's think about what is a category enriched in symmetric spectra with duality. And what this structure is. So when you have a duality, you have a functor from C to C op, okay? And this functor, when you compose it with its op, this would be naturally isomorphic to the identity on this category, okay? So I don't want to do the calculation now, because I want to get to the interesting things. But if you do the calculation of what this means for a category with one object, you will get the correct answer here. Okay? No, I haven't. Okay, so let's think about it. Okay, I don't think it's the most important thing to think about in this context. Okay, so let's assume that this duality is strict. Let's do this. Okay. Okay. So what is this notion of an E1 algebra in symmetric spectra with such an anti-involution, and is it what we're looking for or not? Okay. So the point is that it's not really what we're looking for. Okay. And I want to give some hints as to why it's not what we're looking for, and what the thing we are looking for will be. Okay. So not what we're looking for. So to explain why, let's think about the algebraic context for a second again, and take a ring, just a simple ring with not simple, just a usual ring with anti-involution, and we can take its underlying additive abelian group. Okay, what sort of structure will this abelian group have? It will have a Zemo2 action, right? It will just be an abelian group with the Zemo2 action. Okay, so we said that what we want is an E1 spectrum with a genuine anti-involution. So this should give us an underlying spectrum with a genuine Zemo2 action. Okay, this is not what happens here. We get a Zemo2 action on the underlying spectrum, but it's not genuine. It's a naive Zemo2 action. Okay. We can't say anything about the fixed points of this action using only this information. Okay. So this is one reason why it's not what we're looking for. So the underlying spectrum is a naive Zemo2 spectrum and not genuine. Okay. Okay, so what we can try to do to solve this problem is just start with a genuine Zemo2 spectrum and take an E1 algebra structure on it. Okay, let's try to do that and see if that works. Okay, so attempt. Look at the symmetric monoidal category of genuine Zemo2 spectra and take an E1 algebra in it. Okay? So this solves the problem that we had here. We actually, by definition, we have an underlying genuine Zemo2 spectrum. But it creates a different problem. And the problem here is that the multiplication structure that we're going to have here will make the Zemo2 action, let's say, straight and not twisted, right? It's not going to be a map from A to A up. It's just going to be a map from A to A. Okay? So this is wrong because we get an involution let's call it tau from A to A and not an anti-involution. Okay? So we see that this is close in some sense, right? We kind of want this, but we want a twisted version of this. Okay? So how do we solve this problem? We're going to use to look at the symmetric monoidal category. Still look at the symmetric monoidal category of genuine Zemo2 spectra, but we don't really want an E1 algebra. We're going to want a different sort of algebraic of homotopy coherent algebraic structure. And this is probably the main point of this project, to define such a thing. Okay, just one more thing before I go to actually doing the positive thing. I want to see that there is even more structure that we want out of this, because if we just have a usual ring with anti-involution, we can do all sorts of stuff. For example, we can take norms. Okay, so let's say I have a usual ring with involution. Okay, so I have a map from A tensored with itself to A, which sends two elements to A times B bar. So bar is just the anti-involution. Here, I want an anti-involution. Okay, A to B bar. And notice that if I take a symmetric tensor, okay, then I'm going to get A times A bar. And what happens when I take the bar of this? A times A bar. Bar is A bar bar A bar, which is A bar, which is the same thing. Okay? So, just to summarize, I'm not going to waste all this time again. Sorry for that. So to summarize, we have a map from A, tensor A, to A. Okay, so here we have an involution. Okay, well, not really, but okay. So on the underlying spectra, we have a Zemo2 action here, and we also have a Zemo2 action here that just flips the coordinates. Okay, and if you take the fixed points here, let's call it sigma 2. Okay, if you take the fixed points here, and you take the fixed points here, this induces a map here, right? So what should we call it? Let's call it n for norm, and the norm induces a map here again. Okay, so this is another sort of structure that we're going to want our ring with our ring spectrum with genuine involution to have, and this, of course, doesn't happen in this case, and it doesn't happen in this case either. Okay. So how do you get this structure? How much time do I have? Oh, not a lot of time. Okay, so I'm going to have to do this very, very quickly. Let me see if I can say this very, very quickly. So, as a slogan, the idea is to add Zemo2 everywhere. Okay, just this. We worked in the context of infinity categories. This did not bring us to where we want to go. So we look at Barwick's work, who kind of developed the whole theory of infinity categories from the beginning with a G action. Okay, so he defined what a G infinity category is, what a G symmetric monoidal structure on a G infinity category is, what a G operad is, what an algebra in a G symmetric monoidal category over a G operad is, and so forth and so on. And this is a theory that actually exists and is well developed. And let's say the slogan. Let's just say the slogan, and then I'll see how much I can explain with the time remaining. So slogan. Well, maybe outline. Let's call it outline. So first point is the category of genuine Zemo2 spectra it's first of all, it's a symmetric monoidal category in the infinity categorical sense, but it actually has more structure. Is a Zemo2 symmetric monoidal category. Okay, what does this mean? So I cannot explain, of course, the whole theory, but one thing that it means is that, okay, if I just have a symmetric monoidal category, I think I can think about the data in the following way. Given an object C of this symmetric monoidal structure, symmetric monoidal category, I can produce from it such an object, C to the nth tensor power, okay, where n is any natural number. But because it is symmetric, I don't care about the order of n, so it's actually better to just say that given a finite set x, I can look at C to the x tensorth power, okay? So what is the difference between just a symmetric monoidal category and a G symmetric monoidal category? That instead of just taking finite sets, I can take G finite sets. I can take finite sets with a G action, okay? So how will this help us here? So we can think about just finite sets as sets with a trivial G action, okay? So let's say I have a symmetric spectrum, a genuine Zemo2 symmetric spectrum. Then I can do two things. I can produce from it just a to the tensorth power of how do we call this? Okay. We can produce from it A tensor A with trivial Z-mod 2 action on this. What does this correspond to? It corresponds to taking A to the 10th power of a set of cardinality 2 with trivial G action. Okay? But I can produce from it a different thing. I can produce from it A tensor A with the switch action. Okay? This corresponds to taking A to the 10th power of Z-mod 2 itself as a Z-mod 2 set. Okay? And okay, and what is an E1 algebra structure? At the end, it's based on just a multiplication from A tensor A to A. Okay? But in this case, we will get a multiplication from A tensor A with the switch action to A. Okay? And this will correspond to the anti-involution. But let's explain this further. I have 7 minutes. Let's see how much I can cram into those 7 minutes. Yes. So let's try to speak about G operads. You know what? I can't speak abstractly about G operads in 7 minutes, but I can give you the operad that we want. Okay? Let's give the specific operad that we want. So this is actually related to what we talked about. In a usual operad, non-equivalent operad, we have the spaces of maps that go from a set of size n of inputs to a set of size 1 of inputs. But in a G-equivalent operad, we're going to index our inputs on G sets, on finite G sets, and not just finite sets again. So this is kind of the same concept. Okay. So yeah. So let's say that I have G finite group. And the operad I want to speak about, the G operad I want to speak about, is the following. Let's take rho, finite dimensional representation of G. Okay? And let's take the space, the underlying space. Call it R rho. Okay? And R rho. Okay. And let's take something that is reminiscent of the EN operad. Let's take embeddings of n copies of R rho into R rho. Okay? So this will be, well, I'm kind of contradicting myself now. I will explain so this will be E rho at level n. Yeah, okay, this is something I unfortunately don't have time to explain. It turns out that even though you want to index your operations on G sets, you can actually just give it indexed on natural numbers. I just don't have time to explain this. But this actually gives us a G operad, okay? And this is what we call E rho. But what we have extra structure here, right? We have both G acting here and sigma n. How does sigma n act? It just permutes these cofactors, okay, in the input. And how does G act? It acts on acts by conjugation, first on each cofactor, and then in the end. Okay? So we have both G and sigma n acting here, and this is kind of what defines a G operad. Yes, and And also we need composition, and the composition goes in the exact same way that you know from the usual EN operads. Okay, you just, if you imagine this as disks sitting inside a big disk, and you imagine another such operation, disks sitting inside a larger disk, you can compose like this. Okay. So this is, yeah, this is embedding in the usual sense. Just think of this as a topological space. Think of this as a topological space, and just embeddings of topological spaces. Yeah. That's all we want. So this is actually a G operad. And what happens when G equals Z mod 2 and rho is sigma, which is the sign representation. It acts on R by minus. Okay? So we get an operad called E sigma. Okay? We get an operad, a G operad, a Z mod 2 operad, E sigma. And the thing is that to define an algebra over a G operad, we need an object in a G symmetric monoidal category, not just a symmetric monoidal category. So we take the category of genuine Z mod 2 spectra. It is a Z mod 2 symmetric monoidal category. We ask for an algebra in this category over the G operad, over the Z mod 2 operad E sigma. And this will give us a sort of object, some sort of object. So the claim is, or maybe the suggestion, maybe I should write this. This is important. Suggestion. This, of course, needs to be checked, but this is the direction that we want to go in. Suggestion. So an E1 spectrum with genuine anti-involution should be defined to be an E, keep writing the one here, an E sigma algebra in the Z mod 2 symmetric monoidal category of genuine Z mod 2 spectra. Okay, so what do we want to do from here? And I will just say the big picture, and then I'll finish. So we want to actually check that everything here is defined. We want to consider this category of E sigma algebras in genuine Z mod 2 spectra, and we want to define real THH to be a functor from this category, and we will want to show that any such object gives us, by taking the category of projective modules, a category that might not be an infinity Waldhausen category with duality, but maybe something else, and define real algebraic K-theory on that, and maybe produce a real trace map, and thus generalize the picture that I started with. So I will finish here. Thank you.